Okay, so we've talked about neurons, neural structure, neural communication, nervous system, neurotransmitters. Okay, now we got to kind of put it all together into the ultimate control, like the thing that's in control of everything that we do, the brain. 3 pounds of nerves, fat, water, and then something called cerebrospinal fluid that sits in our skull, surrounded by cerebrospinal fluid and a bunch of capillaries and blood pathways called meninges that are there for cushion. Okay, we're going to talk about the brain. We're going to teach the brain from oldest to newest. We're going to start down here today, and then we're going to work our way up. Now, does anybody have a guess when we say we're teaching it from oldest to newest, what does that mean? Okay, it partially does. Like the part that we're talking about today is the first to develop in humans, like when they're in utero. What else could we be talking about when we talk about teach it going from oldest to newest? Yes, good job. That was the quickest anybody's ever gotten this question. All right, talking about it from evolutionarily. Okay, this part that we're talking about today, called the hindbrain, the reptilian brain. All right, this part we're talking about today, everybody has, and not every animal that has a central nervous system has it. But as we work our way up and we get to this wrinkly area, all right, mammals have this, but it's really only us apes and dolphins and pigs that have them that are this wrinkly. All right, and we'll talk about what the purpose of the wrinkles are. We're talking about it in terms of evolution and how advanced the brain is. All right, so um, before, in the last 50 years or so, we've learned more about the brain than we knew about it in the entirety of human existence before that. Okay, with the advent of new technologies, brain scans, we can relatively easily study the different functions of the brain, different parts of the brain. We still know only a minuscule amount of how it works, but we know a hell of a lot more than we did in 1960. Before that, really, before brain scans, we could really only rely on actual, like, when people damage their brains. Okay, and back in the day, they would go in and we'll talk about later on in this unit, we'll talk about a guy named HM who they went in to destroy an area of his brain to stop seizures. And what they actually found was they stopped the seizures, but he could also no longer form any new memories. All right, they destroyed a part of his brain called the hippocampus. And that was when they were kind of like, oh, well, I guess that part of the brain deals with memory too. So beforehand, that's kind of how we learned about it. All right. And before that, we had to look at damage. And so, Samer, going off what you just said in here, it's just like the guy who had a pipe through their frontal lobe. That is exactly what it is. All right. So we are going to watch. It's about 8 minutes long. This is the thing about Phineas Gage. Gage was the railroad worker that got the tamping iron shot up through his cheek, severed his optic nerve, severed the connection between the frontal lobe and the limbic system, and came out the top of his skull. And he lived. This is really kind of the first time that you see the connection between brain and behavior. I'm going to pause it a few times, ask some questions, but I will give you a little heads up. If you're squeamish, there's one part I've had students pass out during one part before. This video is really old. It's like from the 70s, but it still holds up pretty well, especially with how they describe neurocommunication. Okay, so if you're squeamish, I would say just sit on the couch or something like that so you don't fall and like hit your head anywhere. Okay, all right, so here we go. Phineas Gage. So in that case, what would water be? A placebo. Yep. Okay. All right. So there we go. Phineas Gage. So, it's kind of dramatic or whatnot, but you see how much that the brain damage affected his behavior, although they actually think now that maybe it wasn't as extreme as they said at the time, but they're not sure because this is 1848. Okay, so we are going to talk about four different brain structures today. Okay, we are going to talk about the brain stem, which has three of them, or we're going to talk about the hindbrain, which includes the brain stem and what's called the cerebellum. It's important to note, guys, that even though we talk about all these individual parts and say this part does this part does this, they're all interconnected. Okay, so it's not like everything is as specialized as we make it out to be. That just makes it easier. If we were to say like, well, it kind of does this, but this and blah blah blah. These we have these nuclei that extended. Like it would be impossible to teach for a high school class. But it is way more complex than we are going to make it out to be. But I'm going to try to make it as simple as possible. I can sometimes talk a little bit too much about this because I find the brain to be absolutely fascinating. And I realize that some of you probably find it interesting, but some of you will find it extremely boring. So I'll try to get through them quickly. But if anybody has questions, please feel free to ask. Okay. So, talking about the hindbrain, which includes the brainstem. Okay. Brainstem is this right here. All right. It's where here's the spinal cord, and then it extends up. It's where it expands right here, and it contains the medulla, the pons, and the reticular formation, and some other structures that you don't need to know. All right. So, base of the brainstem is the medulla. Okay. Some of you have probably heard of the medulla before. Maybe if you've seen the Adam Sandler movie, The Water Boy, you heard the medulla oblongata. Okay. The medulla is basically just entirely survival functions. Okay. Controls blood pressure, controls heartbeat, controls breathing, controls digestion, controls sneezing, controls vomiting. All of these different things are functions of the medulla. What do you think would happen if the medulla is damaged? You die. Yeah, yeah, you're dead. Okay. That's why, like, hitting your head right back here, like if you fell back, hit your head, that can kill you immediately because that's your medulla right there. Damaging a lot of parts of the brain, just like we saw with Gage, won't kill you, but damaging the medulla will absolutely kill you. But that's also why, like, if you hear somebody referred to as being brain dead, what that means is all of this, the cortex, is not functioning anymore, but the brain stem, specifically the medulla, is still functioning. Okay. Let's see. So, and this is why some of you may have seen, like, I'm sure a lot of you have heard the phrase running around like a chicken with their head cut off. Right. What that comes from is if you cut off a chicken's head too high up on their neck, it can still survive because their medulla sits like really low. And so if you cut off their head above the medulla, they will still be able to breathe and they will still have a heartbeat. I can't remember what the chicken's name was. I think it was like Tim or something that was a lot that lived for like 2 years without a head. It was like a circus thing. And they actually fed it. They just had an open hole right here. And they actually just fed it with like an eyedropper with food in it. So it just like slid right down its gullet into its stomach. But yeah, so way to remember this, if you damage your medulla, you die. And then, this may help for some. Um, Medulla sounds like Medusa. All right. And what happens if you see Medusa? Yeah, you turn to stone and die. Yep. Okay. So, and in terms, guys, of being able to identify where parts of the brain are located, I'm not going to ask you like specifically where is the medulla, but what we could ask you is, given a diagram with arrows pointing to like here, 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 or here, to say where is the medulla located. The medulla is right down here. Okay, so basically you just need to know the sorry, I have a piece of chicken in my teeth. Um, you need to know the functions, basic functions, and the general area that they are located. What are you talking about, like a zombie, or? Oh, well, so they basically they cut off above like the entire brain stem, and there are some in our brain stem. There is some like some motor control and whatnot, and so instead of, it was basically just like the brain stem sending neural signals still down to the body. I'm not entirely sure, okay, but the chicken's still able to. They're still able. It's somehow still able to send like motor signals for walking down to the muscles. My guess is from the cerebellum, which is what we'll talk about at the end of the class today. So all of this up here is the outside layer of the brain is called the cerebral cortex, which is basically what makes us human and what allows us to think and make decisions and stuff like that. Generally, when somebody's brain dead, what that means is that all of like this area and this area right here, like that has all suffered neuron death, but this area is still functioning. Like this area is, but there's no electrical activity up in the cerebral cortex and the limbic system. Okay. Yep. All right. Now, right on top of the medulla is what's called the pons. The pons does a couple of different things. It is the bridge between the hindbrain, the midbrain, and the forebrain. So it basically lets all of those different parts of the brain communicate with each other. And pons actually means bridge. So if you want to remember, it means bridge in Latin. So if you want to remember that part of it, you could think like a bridge going over a pond. Pond sounds like ponds. Um, Plays a big role in facial expression control. This is where what are called the cranial nerves, which I think there are 13 of them. I used to know all of them, but I don't anymore. The cranial nerves are in the pons or extend out of the pons, and that's what controls facial expressions and movement of the head and face. And then the other thing, its other main function is brain regulation during dreaming. Now, we do most of our dreaming during a specific stage of sleep that we'll talk about later on in this unit called REM sleep. REM stands for rapid eye movement. Most of our vivid dreams happen during this time. Does anybody know what happens to our body during REM sleep? Well, that's in your brain. Yeah, you do. Most of your dreaming's done in REM sleep, but something also happens to our body when we're in REM sleep. Yep. Okay. You are during REM sleep, you are not entirely paralyzed. Your body can still move a little, like you can still have muscle contractions, stuff like that. But for the most part, your body is paralyzed during REM sleep when you're dreaming. Now, why would our body become paralyzed when we're dreaming? So you don't act out your dreams. All right. Now, some people, there is a disorder in which this doesn't happen, and the people like just go like are just like all night like flailing around and like doing all that. But most of us, all right, our okay, hold on, Sammer. So during REM sleep, there's all this activity up here. Our brain looks like it's awake, including sending motor signals down to the body. The pons blocks those motor signals, okay, so that they can't get down to the body and we can't act out our dreams. Now, Sammer just asked about sleepwalking. That's actually in a different stage of sleep. Sleepwalking is in stage 3 and 4 when and our, we only have sleep paralysis during REM sleep. We can dream during the other stages. It's just generally not as intense. Okay. All right. Questions about the pons? What? Yeah, psychologists don't necessarily agree on it. What they do agree on for the most part is that dreams don't really, we'll talk about it later on in this unit, but dreams don't really have any meaning to them. What they think it is just so like when we're during REM sleep, our brain looks like it's awake, which means it's a whole bunch of neural activity, but it's a lot of random neural activity. And they think it's just basically our mind like trying to make sense of that neural activity, which is why our dreams don't make any sense because it's just like all over the place. We'll talk about it later on this unit though. All right. Well, how would you know? How would they know? Yeah. Okay. All right. Now, within the brain stem, it's inside of the brain stem and it kind of comes up like this. And you can't actually see it because it's actually just a network of nerves. What is called the reticular formation or the reticular activation system. The reticular formation plays a big role in controlling arousal, which is like wakefulness, not when we say arousal in this class, it's not always like sexual arousal. Okay. Controlling arousal, wakefulness, and focus. Okay. Being able to, our ability to filter out unnecessary stimuli in our environment. Basically, with stuff coming in, the reticular formation helps decide what we should be paying attention to and what we shouldn't. What's called selective attention. Now, who in here has ever like been in a party or whatnot in a loud room and you're talking to somebody and you're focused on them and then all of a sudden out of the corner of your ear you hear somebody say your name like across the room? Anybody ever? Or you're talking to somebody and there's another conversation going on behind you and you hear part and something like really like you hear something that sounds like a little interesting, you're like who hooked up with who, like, and your attention like entirely shifts over to the other conversation. Yeah. Okay. That's called the cocktail party effect. All right, we'll talk about it next unit. That's the reticular formation that helps us do that. Okay. What disorder do you think the reticular formation would play a role in? If it, ADHD. Yep. Not only this, ADHD also has a lot to do with the reward system in our brain, in the limbic system. But ADHD, this plays a big role in ADHD. Okay, so stimulated, you're awake, all right, damaged, you can go into a coma. All right, not dopamine does probably have a little bit of a role in the reticular activation system, I would imagine, but dopamine is more prevalent in an area of the brain up here called the reward pathway, that we'll talk about next class. But I'll look that up. I've never seen with the reticular formation and dopamine, but I'm sure that it does. That's a good connection there. All right, so here's a quick video. We're going to see these psychologists stimulate a cat's reticular formation. Just so for you animal people, no animals were harmed. Like, this doesn't hurt the cat. We don't have any pain receptors in our brain, so the cat can't actually feel anything that's going on. Okay, but you're going to see what the activation of it looks like. Okay, so there you go. Here's the reticular formation. All right, any questions about that? We got one more. All right, now, sitting behind the brainstem, this is still part of the hindbrain, but is not in the brainstem, is this large brain-like structure at the base of the skull right here called the cerebellum. Okay, cerebellum in Latin means little brain. This part of the brain is involved heavily in balance, voluntary motor movement, and coordination. Coordinating movements. Okay, for instance, everybody stick your hands out like this, point your fingers out, and close your eyes. Now, touch your nose with your right hand. All right? Touch your nose with your left hand. Touch your left ear with your right finger. Right ear, left finger. Now, still with your eyes closed, try to get your two fingers to touch in front of you. Should only take like one or two tries, and then you should be pretty good after that, unless you're drunk right now, which I don't know, you might be. You're at home. Okay. All right. That's the cerebellum. That allows you to do that. That's why they do, when they do sobriety tests, they have them do stuff like that because alcohol has a big effect on the cerebellum. People with what is called cerebellar ataxia have a really hard time doing that. So here's a quick video. So you can see there, he just has a hard time because it damaged his right side of his cerebellum, so it affects his left hand or whichever one it was. This is where when we talked about like with dopamine and Parkinson's disease, this is where like the cerebellum has a fair amount of dopamine in it, and with dopamine and Parkinson's disease, it has a lot to do with making movement smooth. All right. And that's like what those tremors affect that. That I believe is the cerebellum. This also plays a big role in telling the body what to expect from movement. So can anybody in here tickle themselves? Like you just sit there and like stop tickling me. Stop like okay, can anybody tickle themselves? Yeah, Landon, you can. Like yeah, like you might be able to tickle yourself like this, but like you know when if you're tickling like a kid and you get all up in like you're like most of us probably can't do that, right? Why can't you tickle yourself like that? Anybody have a guess? Huh? Oh yeah, I don't know. Oh, Connor. Yeah, because your brain's telling your hands where to go. So whether you realize it or not, like your brain knows where your hands are going to be, and that's part of being tickled. Like it's like the kind of like not knowing where the tickling is going to be. Getting tickled is miserable. So, all right. Last thing was cerebellum. Um, you would damage to it, you lose motor control, such as if you could play the guitar before, you might not be able to play the guitar anymore. And it also affects like automatic, like well learned. I don't know why this thing like writes like this. Well learned movements. So like being able to play a sport and being good at a sport to the point where like you don't really have to think about it, you can just do it. That cerebellum plays a big role in that. What is that called? Muscle memory. Cerebellum is where most of our muscle memory is stored. Mm-hmm. Yeah. Yeah, we can. You can. I think I have a video similar to that. If you find that video, send it to me because that's really cool. Yeah, you can have brain surgery. Most of the time when they do brain surgery, the patient is entirely awake, is awake, because you can't feel anything in your brain. So, okay. Any questions there? All right. I'm about to let you go and take the quiz. All right. So the quiz is right here. Okay. I'm going to let you just go and take it. Oh, thank you, Aiden. Okay. Let me click on that so I have the link. Oh, and I got to